But each part of these machines, we can call it a mechanism. For example, due to the chemical energy, burnt of chemical energy explosion of diesel or petrol, there is a reciprocation of piston cylinder takes place. So that is a reciprocating motion. Now from this reciprocating motion, actually, we convert into a rotary motion. Now this is a particularly we use a particular mechanism called crank connecting rod mechanism. Now that is a mechanism. For example, differential gear box, where motion is transmitted to the two tires, okay, of the rear wheel. Now that is a mechanism. A part of that machine could be a mechanism where motion is being transferred. Okay. Also force is being transferred, but in our kinematic courses, okay, we'll talk about motion only. We'll exclude the force part, okay, and that we can do actually. Even if you don't consider the force part of the machine or for a mechanism, we can analyze the motion part. That means velocity, displacement, acceleration, we can analyze it, okay. And that gives, I mean, whenever we consider about the force part, we call it a dynamics, and whenever we call only the motion part, we call it a kinematics. Now that Vitruvius, a military engineer about 28 BC, that means before Christ, defined a machine as a combination of timber fastened together, particularly effective in moving great weights. About a century later, that's a little bit history I'm giving it. About a century later, hero of Alexandria, a mathematician, not the Alexander the Great, that is 10 AD to 70 AD, summarized 5 simple machines for moving a given weight by a given force. They are levers, windlash. Windlash is basically a mechanism by which you can wind, unwind thick cord for generally used for ship industries. Screw for power transmission, wedges. By using the wedges, you can lift certain things, and tackle block. Actually, we call it a pulley. Nowadays, we know known as a pulley. It was known as tackle block. So he gives 5 as the machines. Okay. Until early the end of the 19th century, it was held that these 5 mechanical powers were the building blocks from which all more complex assemblies were constructed. Euler, along with his partner D'Alembert and Kant, suggested the separation of geometrical mechanical aspect to simplify the study of motion of rigid body. This is very important thing, that separation of geometrical and mechanical aspect, so that we can study everything as a rigid body. If we consider a body as a rigid body, then the total problem becomes simpler, but we don't lose much from the result point of view. Some accuracy we lose, but the problem becomes very simple. Bunge, that is 1746 to 1818, the inventor of descriptive geometry. You have a course on descriptive geometry, right? Bunge,
we have completed that course.
Yeah, Bunge actually invented that in elements of machines and started the task of classifying all the then available machine and mechanism. See, people at that time, they were versatile. They used to work in different fields. Hatchett completed his work in 1800, and Ampere coined the word kinematics from the Greek word for motion, which was later anglicized to kinematics. Okay, that from here we got the word kinematics of machines. Now, other notable text on this was Betancourt, Coriolis. that Coriolis forces and Coriolis acceleration comes from him. He gives that first concept of the Coriolis acceleration. We'll be talking about this also in our acceleration analysis. Robert Willis, in his book Principle of Mechanism, made an attempt to summarize, systemize the task of mechanism synthesis. There is two parts in this course basically. One is the analysis part, another one is the synthesis part. I can give you some example. For example, that suppose windshield wiper of a automobile. Now we used during rain. Okay. Now this wiper actually is a mechanism. Now suppose you want to design a wiper. Now what are the inputs we get from the user? That is, what should be the speed of the wiper and how much area it should cover. Okay, that you can get. Now in order to, and what you have to do as a designer is you have to design that wiper. That means so that it will move in that speed and it will cover that much surface area of the windshield. Okay, now so this is a reverse process actually, because in the first part of this course, what we will do is we will assume a mechanism. It is doing this kind of work, or this kind of motion is being transmitted, and we will try to analyze the velocity and acceleration. The second part is that we need this kind of velocity and acceleration. We have to design the mechanism. That is the synthesis. Now, as a designer, we are more interested in this synthesis part only. But in order to have that synthesis part, in order to have that expertise to build a synthesis, you need the analysis part, expertise about the analysis part. So first half of this course will be, not the first, majority of the course will be analysis and some of them will be synthesis. Okay. Now, so Willis actually counted the 5 ways of obtaining relative motion between the input and output members: rolling contact, sliding contact, linkages, wrapping connection, and tackle. Tackle means that pulley again. Okay. Now, origin of kinematics of machine, Franz Roulet. He was born near Aachen, Germany on September 30, 1829. He is regarded as the founder of the modern kinematics and as one of the forerunner of modern design theory of machines. Okay. The modern theory of machines started with the book. It was written by Roulet, The Kinematics of Machinery, Outlines of a Theory of Machine. He has written it 1875. The book is so original in concept that the ideas that Kennedy immediately translated it into English in 1876. So basic work was done by a German scientist, Roulet. The most important ideas propounded in this book, which still form the backbone of the modern text of theory of machines, are kinematic pair, kinematic chain, and kinematic inversion. So he gives 3 basic parameters to define a mechanism. One is kinematic pair, one is kinematic chain, and kinematic inversion. We'll come to them during our course of time. Besides his influence in kinematics, Roulet was active in the technological politics of the newly united German Empire. He had an important role in developing German patent legislation. He founded Mannesmann Steel Works, acted as a member of the juries of the international exhibitions. Thus, Roulet was active in improving the quality of German manufacturing. See the versatility of a person. In 19th century, kinematics flourished because of the need for the machine inventors to transmit motion and forces. In 19th century, there was a renaissance. Okay, from one element, so the newer and newer machines were invented. There was some printing machine came. Then James Watt and Rankine found the steam engine. James Watt didn't invented steam engine actually. He developed a steam engine such that it can be useful for doing some work. Now, for all this machine, we required mechanism to transmit motion so that it could be useful to us. Okay. So naturally, the invention of machines, so many mechanisms has been developed. Okay. Now, what's straight line mechanism? It seems, I mean, by this mechanism actually, it's a linkage mechanism, you see. There is a gear arrangement, there is a linkage arrangement. So with this linkage arrangement actually, this will move in this way, okay. This will oscillate, this bar will oscillate. As a result, what will happen? This point in will move in a straight line and it will move up and down, which actually is useful for the piston cylinder movement. Now, before that time, not good machineries were developed for metal cutting. So straight line mechanism now, I mean, it's very difficult to find something that one point will move in a straight line. Nowadays we can make a straight cut with the help of machines and you can easily do it, but that time it was not there. So it was a real good invention actually. According to a letter written to his son, he was most proud of this mechanism among all the inventions. Several generations of researchers have worked on this problem of straight line generation, not merely copying the existing one, using planar and spatial linkages. A paper has been published to this topic even in 1994. You see that still straight line mechanism, it attracts so many scientists, so that the paper has been published in 1994. Now, so there was a library in which they have conserved some of the mechanism which has been taught in the Rule's book. Okay, I'll talk about this in my next slide, but let me tell about this. One is screw kinematic pair. This is a screw pair. Okay, see this term kinematic pair. He has introduced the term kinematic pair. That means a pair of material by which motion is transmitted from one to another. That is called a kinematic pair. Okay. Then turning pair, sliding pair, then four-bar linkage mechanism, slider car mechanism. All these models has been kept conserved. Now this is actually worm and worm wheel mechanism. Okay. So endless screw mechanism was featured. See, you see that this is actually real mechanism, and this is a picture drawn by Leonardo da Vinci. That is another genius actually. That time he didn't develop that mechanism, but he had an idea that this could be possible, and it's a drawing done by him, okay, of this mechanism. That's way long back. Now, then some rotary pump mechanism was described in 1588 by Italian military engineer Agostino Ramillo. See, I have used a term military engineer, right? Actually, you'll find that in history, that military engineer comes first actually. That means people, the engineers or technology people who are involved in the warfare industries. We used to term them as military engineer. And later on, we find another bunch of engineering come who are used for the civilians. They used to make things for the civilians, and that word civil engineering comes. So first we came the word military engineer. From there we came actually the word civil engineering. Okay. So now there is some gear pump. This is called a gear pump, in which we can transmit motion, I mean fluid from here to here, actually, with the help of two gears. Then now this is another very good examples of mechanism was that pendulum clock, crown wheel escapement. Now Huygens, who designed the first pendulum clock in 1657. Now, if you see the inside of an old grandfather or grandmother clock, you will find that there are so many mechanisms in which the energy stored is being transmitted to give motion to the minute hand and the second hand and the hour hand. Okay, so then this is a spar gear mechanism, simple spar gear mechanism. Then there is a complicated planetary gear mechanism. Okay, we'll talk about it. This is a Geneva mechanism in which we can convert intermittent motion okay, now the analysis part of the 4-bar, see, I'll talk about the 4-bar, some analysis part of the 4-bar mechanism or any other mechanism first used with the graphical method. Will give some idea about the graphical method also to you, and later on that analytical method came, okay, with the advancement of the computer basically. I think then the modern era, in the last 4 to 5 decades, the operating speed of various machines had to be increased in order to raise productivity. The level of accuracy to be achieved in the required motion of characteristics also increased substantially. As a result, elements of machine can no longer be designed on the basis of rigid body theory. Consequently, the kinematics and dynamics cannot be treated separately. Now, in this course, we will be treating kinematics and dynamics separately. But in actual practice, we have to consider the dynamics also. Machine components under sufficient deformation so as to change the kinematic dimension. This in turn change the acceleration and the inertia forces on various components. The subject areas like kineto-elastodynamic were developed. Use of digital computer has decreased the importance of earlier graphic techniques for solving problems in the areas of both kinematic analysis and synthesis of mechanism. But still, graphical techniques are very important to have a good idea or the concept about the subject. With the advent of computer graphics, animations of mechanism movement on the computer screen is gradually replacing the model and prototype building for checking the performance of a design mechanism. Systematic analysis and synthesis of spatial linkage were facilitated with the publication of Bayer's book 1963 and the development of Genevieve-Hartenberg's matrix notation. Here's a tremendous application, this notation in robotics. And use of homogeneous coordinate transformations. Okay, he gave these two concepts, that notation and the homogeneous coordinate transformation. Actually, robotics is nothing but 3D kinematics, 3D mechanism. Use of dual number quaternion provided some alternative mathematical tools for study of kinematics and dynamics of spatial linkage consisting of rigid body. For example, complex variable we can apply here. Shortly after this development arrived the age of robotics and programmable automation. Now, we'll have some idea how to tackle the problem analytically, okay, in this course. And you have another course on robotics, where you will be dealing with this Genevieve-Hartenberg's matrix, homogeneous transformation, but this homogeneous coordinate transformation is highly used in computer graphics also. The mathematics is same for the robotics and the computer graphics. Okay. Now the books I'll be following is Theory of Machines. So this is the modern era. Okay, now this course is a transition of the modern era and the previous graphical analysis also. So mainly recommended books are Theory of Machines and Mechanism and Machines by Amitabh Ghosh and A.K. Mollik. In fact, A.K. Mollik is my teacher. I did my PhD under him. He's a damn good teacher of Kanpur IIT. Both of them are from Kanpur IIT. Elements of Mechanism, Doughty and James, that is the graphical method. It's a very good book, okay, to have an earlier idea on mechanism. Mechanics and Dynamics of Machines, maybe and Reinholz. I think you'll have some copies in the library. Then Mechanism Design, Analysis and Theory, Volume 1 and 2 by Erdmann and Sander. Mainly 4 of this book I'll be covering. And you can also consult Rotten book and Theory of Machines by Sigley. There is a very good book. I mean, it was what else? Kurmi, you can consult. Okay, but if you want to buy any book, buy this Ghosh Mollik's book. Okay. So, any questions so far?
It means that we can either go for a Ghosh and Mollik or S.S. Ratan.
Yeah, I will prefer Ghosh and Mollik, but
okay, sir, okay.
I'll give handouts also. But
okay, sir. Okay, sir.
For the problems and other things, you have to consult some book for this course.
Yes, sir, for the theory part also. Okay, sir, surely.
Yeah. So, with this introduction, I will start my first class. Okay. Linkage mechanism. Now, as you see that when James Watt developed his machines, he used so many linkage mechanisms. Even in the automobiles, actually the development of mechanical engineering started with these machines and the development of automobile engineering. And with the progress of the
sir, to sir screen ke sath zoom kora jabe dekhte osubidha hocche
zoom
full screen kore sir bhalo.
Okay.
Thank you sir. Okay sir.
Now this is okay, or is this okay?
Yes sir.
Yes sir.
Okay. Now so with the development of newer and newer version of car, you'll find that so many inventions take place in the process. Okay, and it's mainly mechanical engineering inventions. So we'll start with, and in the previous case, the linkage mechanism plays a very, very good role in developing so many mechanisms. Nowadays, with the help of servo motors, development of servo motors, the importance of linkage mechanism has reduced a little bit, but still it's there. Now, what is a link? A link is defined as a rigid body having 2 or more pairing elements which connect it to other bodies for the purpose of transmitting motion, force or motion. That means I can tell you. See, this is a linkage mechanism. This is one link, this is another link. They are connected by some means. Okay, this connection could be different ways, but we call them link. Okay, and this is a part of a linkage mechanism. Let's come back to this one. Now, for a mechanism, we have to have a fixed link. In every machine, at least machines or mechanism, at least one link either occupies a fixed position relative to the earth or carries the machine as a whole along with it during motion. This link is the frame of the machine and is called the fixed link. Okay. Now this cycle, basically, you see this is a linkage mechanism basically. And you see this member, This is a 3-bar member basically. Okay, this is a 3-bar member. This is a fixed link, or we call it a structure. Now, this is a 4-bar linkage mechanism. You see, 1, 2, 3, and 4. 4 linkages there. They are connected by pin joints. Okay, there are pin joints. So, and you know that whenever there is a pin joint or hinge, we call it it allows motion between these two members in the angular direction only, not translation or any other direction. And in order to run this mechanism, you find that we have to fix one mechanism to the ground. So we can fix any one of them. Now, if I fix this one, we'll find that, but still there is some hinges here. There are 4 hinges. Now, if I give a motion to this mechanism, okay, if I give a angular motion to this mechanism, that this will pull this one as a whole. This will also be pulled. So motion will be transmitted from this mechanism, this link to this link. Now, individually, all this, it has a 4-bar linkage mechanism, we call it. Okay. Now, and these links are called binary links because we can add only 2 links at the 2 ends of this link. Okay. Now, there is another term called kinematic pairs. A kinematic pair is a combination of 2 kinematic links that have relative motion with respect to one another. When 2 links or elements in a machine are in contact with each other, they form a pair. That means this pin joint is a kinematic pair. Okay, and it allows only angular motion between them. When the relative motion between these 2 links is completely or partially constrained, then the links are said to form a kinematic pair. Now, any member will be free to have 2 types of motion. One is translatory motion. If it is in a single plane, this is another thing I'm talking about, that we are talking about a planary motion now. Okay, in most of the time we'll be covering plane motion. That means all the motion is being considered in a one plane. Now, so if a link is there on a plane, then it can have 2 types of motion. One is translatory motion, one is angular motion. Now, a kinematic pair, that pin joint only allows rotary motion or the angular motion between the 2 linkages. Okay, so it's giving a constraint to the translatory motion, and that's why it's called a kinematic pair. Now, degree of freedom of a kinematic pair is given by the number of independent coordinates required to completely specify the relative motion. There are certain terms I have introduced. I'm not thoroughly explaining those terms now. For example, degree of freedom, I will take a full class on degrees of freedom. Now, in gist, what is this meaning of this sentence is that this pin joint will be allowing only 1 degree of freedom. That means it will allow only rotary motion between the 2 linkages. Okay, so now there are different kind of kinematic pair, and 4-bar linkage mechanism is the simplest type of mechanism possible which can transmit motion, because if we form a mechanism with the help of 3-bar, then it will be a triangle, and from your common sense you can find that it's not possible to have any motion between these 3 bars. That's the fixed member, and we call it a structure. So in order to have a mechanism which can transmit motion, we will have at least 4-bar. Okay, so 4-bar mechanism is called the simplest type of mechanism. Now let us talk about the kinematic pair. We have already shown one kinematic pair, that is a pin joint. That means there are holes here. Through these holes I can put a pin. These pins allows motion between these 2. An example of a pin joint is the hinge of a door. Okay, you will see that's the pin joint. Now, also we call them revolute pair. A revolute allows only a relative motion between element 1 and element 2, which can be expressed as a single coordinate angle theta. So this angle theta we can, so single coordinate, and it will have a single degrees of freedom. Thus a revolute pair has a single degrees of freedom. Example of revolute joint is this one. See here, should I enumerate it? This is a pin joint. Okay, so what it allows, a pliers motion between these two, and if I give a motion here, I can transmit motion here. Now this is a sort of pin joint. Okay, single freedom possible in our elbow. And this is also, see, application of pin joint. I can move this one up and down with the help of this pin joint. Okay. Prismatic pair. Now, a prismatic pair allows only relative translation between element 1 and element 2, which can be expressed by a single coordinate s. See, this is a prismatic joint. It has a prism type of structure, and there is a slot in this one, similar slot. So if I put on this, I can move this one with respect to this one in this direction. So it will allow reciprocation motion. The example is shown here. Okay, thus a prismatic pair has a single degrees of freedom. Now you see what is the difference between this one and this one. Here only rotary motion is possible. Here only translatory motion is possible. No rotary motion is possible between this one and this one. Okay, and it has a single degree of freedom because only translatory motion is possible. Screw pair. A screw pair allows only a relative movement between these two elements, which can be expressed. Now, suppose if I give a rotation of this knot, if I fix this one, then the knot will move in the forward direction. Now, in the first hand, you will have a feeling that it has a 2 degrees of freedom because I am giving a rotation. At the same time, it is advancing in these directions. So it should have a 2 degrees of freedom, but actually it has a single degree of freedom because there is a relationship between the rotation and the translation, which is governed by the pitch of this thread. Okay, these two coordinates are related by theta by twice pi is equal to s by l. So it has a single degrees of freedom. So this is called a screw pair. Cylindrical pair. This is a cylindrical pair. A cylindrical pair allows both rotation and translation. For example, if this prism, if instead of this is a circle, then what will happen? I can, and this slot will also be circle, then what will happen? I can move it in this translation direction. At the same time, I can rotate it. So this is nothing but the cylindrical pair. Okay. As a cylindrical pair has, yes.
স্যার বলছি তাহলে স্ক্রু যে এটা দেখলাম ওটাতে তো স্যার আমি ঘোরালে তো ওটা আমি ঘোরাচ্ছিও অ্যাকর্ডিংলি ওটা উপরের দিকে বা নিচের দিকে উঠে আসছে, তো ওখানেও তো রোটেশন এন্ড ট্রান্সলেশন দুটোই হয়।
আমি সেটাই বললাম, কিন্তু এইখানে কি আমি ইন্ডিপেন্ডেন্টলি দুটো জিনিস কন্ট্রোল করতে পারি। মানে আমি যেটা রোটেশন দেবো সেটা আমি আলাদা করে কন্ট্রোল করতে পারি, আমি ট্রান্সলেশনটাও আলাদা করে কন্ট্রোল করতে পারি সিলিন্ড্রিক্যাল পেয়ারে। এখানে কিন্তু সেটা আমি পাচ্ছি না।
ওকে,
মানে আমি এখানে যা রোটেশন দেবো ও অলরেডি পিচ দ্বারা, মানে পিচ উইল বি ডিসাইডিং ফ্যাক্টর হাউ মাচ ইট উইল অ্যাডভান্স। ওকে, সো দ্যাটস ওয়াই ইটস এ সিঙ্গল ডিগ্রি অফ ফ্রিডম সিস্টেম। মানে আমি এই রোটেশনটা দিয়ে আমি এর অ্যাডভান্সমেন্ট ইন দ্য ট্রান্সলেশন ডিরেকশনটাকে কন্ট্রোল করতে পারছি। মানে আমি জানি যে কতটা হবে, আমি ইন্ডিপেন্ডেন্টলি ওটাকে করতে পারছি না। যতক্ষণ আমি ইন্ডিপেন্ডেন্টলি কন্ট্রোল করতে পারবো তখনই ওটার ডিগ্রিজ অফ ফ্রিডম বাড়বে। ওকে, so this is an example. Lead screw of a lathe is an example. Spherical pair. A spherical pair allows 3 degrees of freedom since the complete description of relative movement between the connected elements needs 3 independent coordinates. 2 of the coordinates alpha and beta are required to specify the positions of the axis OY, and the third coordinate theta describes the rotation about the whatever. But this is a spherical pair. Okay, it has 3 degrees of freedom. Hip joints is a example of 3 degrees of freedom spherical pair. Okay, now based on the nature of the contact between the pairing elements, we define 2 terms, lower pair and higher pair. What is a lower pair? When connection between the element is through area of contact. That means, for example, pin joint, the connection is area of contact. We call it a degrees of freedom is 1. We call it a lower pair. And higher pair is when connection between the element is through a point or line contact. I'll give the example of higher pair. Cam and follower mechanism, gear pair, those have a line contact. Okay, when I will give the example of that, I will talk about, because cam follower will be talking about, gear pair will be talking about in this course, and it generally degrees of freedom will be 2 and above. Okay, so those are called higher pair. Now, kinematic chain, the combination of links and pairs without a fixed link is not a mechanism but a kinematic chain. For example, cycle is a chain, that is a kinematic chain. We find that each one of them, how the cycle chain has been formed is by the binary linkage, and all the binary linkages are connected by pin joints. But as such, until and unless you put the chain on a sprocket, okay, it cannot transmit motion. So it doesn't have any fixed link, but it will be useful for transmitting motion. Okay. Now, what is a linkage mechanism? A mechanism composed of rigid bodies and lower pairs is called linkage mechanism. Function, main function of link mechanism is to produce rotating, oscillating and reciprocating motion from rotation of crank and vice versa. I'll give example. Link mechanism can be used to convert continuous rotation into a continuous rotation into a oscillation or reciprocation, oscillation into oscillation. I'll give example, then it will be clear. Okay. Now, this is a 4-bar linkage mechanism shown. See, I can feel what is there is, this is a hinge joint or pin joint, this is a hinge joint, this is a hinge joint, and this is a hinge joint. You can see there are 3 members, 1, 2, 3. Now, and I can assume always there is a member between them. Okay, which is a fixed member, fixed to ground. As I mentioned earlier that for any mechanism, one member has to be fixed to the ground in order to transmit motion. Now, this is a 4-bar linkage mechanism. If this member 2 can turn completely, we call it a crank. Okay, if we turn this one, okay, if I turn this one completely, it will, suppose I have given a 30-degree rotation. Now, depending on the length size, it will have some rotation, may not be 30 degree. When it will be 30 degree, if this link and this link is same, then if I give a rotation of 30 degree, this will have a 30 degree rotation. Okay, this is link 3, we call it a connecting rod. because it's connecting two cranks. Since this is also rotating about the fixed point, these are the two fixed points. These are moving points. Okay. And this is called a binary linkage mechanism. Now, so there are link 1, 2, 3, 4, 4 linkage mechanism, and we already defined that this is the simplest possible linkage mechanism. For the time being, we assume that all of them are rigid bodies. Okay. Now, so if I give a motion, I'll get a motion here. However, there's an interesting phenomena that depending on the size of this dimensions of this linkage mechanism, I can have different rotation or different movement of this link 4. How? Let's see. And that depends solely on the dimensions of this one. That is very interesting. Nothing else. How much velocity or acceleration it will have, it doesn't have any implications. Okay. That's what actually Roulet or whoever I said mentioned, that he defined first that dimension we can separately treat here. See, this is a 4 example I am giving. Depending on the length of the links and the positions of the fixed link, the mechanism may have in different fashion as shown below. For example, if this is the dimensions, we find that if I rotate this one, you rotate, then L will rotate completely. Okay. We call it a double crank mechanism. Now, if this is the size of the mechanism, then what will happen? This will move in this direction completely, but this will oscillate in this direction. It will come at the end of this one, and then it will come back to this one. So we call it this mechanism, we call it a double crank mechanism. We call it a crank rocker mechanism. This is a double rocker mechanism. That means both of them will oscillate. This will oscillate in this direction. This will oscillate in this region. And we call it a parallelogram linkage mechanism. That means all of them are parallel. If I give a rotation here, it will have a complete rotation. That is double crank mechanism. Now, any idea, suppose this is a mechanism, crank rocker mechanism. Any idea how I can find out? Suppose all the dimensions are given. How to find out the extreme positions of this one? There are 2 ways to do it. One is analytically, we can tell you. Another one is graphically, we can define the extreme positions. Can you suggest, can you tell me how to find out graphically the extreme positions of this? Any suggestion? No suggestion.
So by looking at that smaller circle and finding the extreme position of S link, and then determining that same angle will be covered by that.
Angle won't come here actually as such, but length will come definitely. Now, what will be the positions of the linkages at this one extreme and another extreme positions? Any idea? When suppose this is one extreme position I am mentioning. So what will be the positions of these two linkages that time?
So which two linkage?
When it will be
F and L.
furthest from these positions. Yeah, and they will be in straight line actually. One straight line. Hmm. Hmm. No, but I want to find out graphically this one by drawing.
Sir, in the
basically by
right, sir, at the rightmost extreme,
calculation.
sir, at the rightmost extreme, L and S will be in a straight line, and the leftmost extreme, the linkage S will actually become horizontal.
Exactly. No, not horizontal. Think over it a little bit. Okay, let us first, whatever, the first part, whatever you said is correct. That means, but how to find out graphically this one? By drawing. Suppose I have the link lengths. And this position, two positions have been mentioned already. Now, what will be the movement of this point? It will be on an arc. I draw this arc. Okay. So naturally, this point will have, because it's moving about the center, it cannot have any point other than this arc. And what is another condition? That when it will be extreme, these two lines will be straight line, right? So what I do is, I add this one plus this one and take an arc and cut it here. And then that will be the point at which it will be extreme. And what will be the positions of the linkage mechanism? It will be straight. Let's see this one. You see, these are two extreme positions. One will be B, what is it? BA or B, whatever is given here. Now, what will be the corresponding positions of A then? It will be here, A0, and it will be at B0. So, what I do is, I draw an arc here. I add this length plus A plus B. I take a AB arc and cut it here. So that will give the one extreme position. What will be the other extreme position? Other extreme position will be B1 when actually AB will overlap on A. So what will be the distance from here to here then? I take B minus A and then draw an arc here and cut it here. So that gives another extreme positions. And what will be the positions of the mechanism that time? It will be, this will be here, then AB will be like this, and then this will be the rank. Okay. So, graphical problems, complicated problem very easily. But and remember another thing is that depending on the size of this mechanism, the angle covered by this crank and this crank will be different. That will be also will be using in our steering mechanism. Actually, still in ambassador car they use this kind of mechanism for steering the wheels. Okay. So do you have a class? Yeah.
Yes, sorry to interrupt, sir. We have a class from 11.
Okay, so I'll finish right now, I guess. That will be better.
Yes, sir. Yes, sir.
Okay, so tomorrow we'll start from this point. And I'll send these two notes to you. Okay, by mail.
Okay, sir. Okay, sir.
Okay, sir.
And come.
Okay, sir.
Okay, thank you.
Thank you,
Thank you, sir.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you.